In linear algebra, a really important concept is that of linear independence. We've seen this at play already, though we haven't had the structure yet to implement it. So in this video, we're just going to look at the definition and kind of the key idea. Before we get into the definition, though, I think it's important to have a sense of geometric intuition. What's really going on when we talk about linear independence? So when you see the word independence, it's natural to want to impose your own definition on it based on how you've seen the word used in real-world context. But it's a little bit different in linear algebra. So hang with me here as we try to unpack what this term means. So in geometric terms, a collection of vectors. Okay, so we're dealing with one or more vectors. So it's a collection. Sometimes instead of the word collection, we'll use the word set. Set and collection mean the same thing. It's just a collection of them. Is said to be linearly independent. All right, so that group of vectors is said to be linearly independent if it is not possible to place multiples, okay, so not all zero multiples of the vectors together, tip to tail, and arrive back at the origin using only the remaining vectors. So basically the idea is that if we can start at the origin and we can scale one of the vectors and scale the other vector, and maybe we have three vectors and we scale the third vector, and it's not possible to scale it in a way that we arrive back at the origin without reusing some of the other vectors, then that set is deemed linearly independent. If, however, it is possible to say leave the origin and then use the final vector to take us back to the origin, then that set of vectors is called linearly dependent. If it is possible to do so, then we call those, like I said, linearly dependent vectors. So as the first example, let's say that we have these three vectors in two dimensions, 1, 0, 0, 1, and 3, 2. This collection / set of vectors is linearly dependent. So what we're implying here is that it's possible to apply multiples of these vectors, not all 0. Okay, so some of them can be 0, but not all of them can be 0. And it is possible to arrive back at the origin. Okay, so imagine for a moment that these are three modes of transportation. The first mode of transportation will allow you to go 1 mile east and for every 0 miles north. So you can only travel east or west using this 1, 0 vector. If you apply a positive scalar, you'll move east. If you apply a negative scalar, you'll move west. So let's actually give this the cardinal directions north, east, southwest, like a compass. So 1, 0 will allow you to travel left or right. 0, 1 will allow you to travel anywhere up or down. And 3, 2 will allow you to travel proportionally 3 units east to 2 miles north, or basically a 3 to 2 ratio. Now, if I ask the question of, okay, is it possible to apply multiples to these and arrive back at the origin? There could be more than one way to do it, but I'm just going to propose one such way. So with the vector 1, 0, I can leave the origin, and perhaps what I'll do is just take a multiple of 1 to that vector. Okay, so that will take me to the point 1, 0. So this is the representation of 1 times 1, 0. So in this case, my multiple is 1. Now, if I take 0, 1 and do the same thing, you know what? Actually, in fact, let's not do a multiple of 1. Let's do a multiple of 0 of 3. So that will take me, if I take 3 times 1, 0, that will take me over here to the point 3, 0. So this is 3 times 1, 0. So our multiple now is going to be 3. And if I take the 0, 1 vector and I take 2 times that, placing it on the tip of this vector, that'll take me to the location. Do this in a different color. If I take 2 times this guy, that'll take me to a north position of 2. And if you notice, 3 times 1, 0 plus 2 times 0, 1 is 3, 2. So I'm at the location right now, 3 units east, 2 miles north. And now if all I have left, as I go through this, I can't reuse those vectors again. I can only take one multiple of them, and then I have to give up that mode of transportation and then move on to the next vector. The question I have to ask myself now is it possible to return back to the origin, to return home with just the 3, 2 vector? You might see this already, that it is possible to do this, because if I'm at the position 3, 2, then I basically have to move left 3 units and down 2 units. So now, taking a -1 multiple of the vector 3, 2 puts me back at the origin. So notice this triangulation that we're getting here. We are taking 3 times 1, 0 plus 2 times 0, 1 plus, I'll write it as plus -1 times 3, 2. And where does that place me? Well, that places me back at the origin, which in vector form we'd write as 0, 0. So in this case, it is possible to place multiples, not all 0, of the vectors together, tip to tail, and arrive back at the origin using only the remaining vectors. So I've only used each vector once. We can see that here. I've taken one multiple of each vector, and I've been able to get back to the origin. So because I can take multiples, in other words, if we label 3 to be our first constant, and the 1, 0 vector to be our first vector, and we take 2 to be our second constant, and 0, 1 to be our second vector, -1 is our third constant and our third vector, and we add these together, we see that it's possible to get back to the origin, which a lot of times we'll just write as the 0 vector. So in this case, I'm going to write mathematically, there exist C1, C2, C3, not all 0, right? Because one way you could say that you could get back to the origin is to just make C1, C2, and C3 all 0 to begin with, and then you would still be back at the 0 vector, but the idea is that you have to be able to leave the origin. So at least one of these vectors has to have a non-zero coefficient. And I've done that actually on all 3 of them, so I've totally maxed out in that case. There exists C1, C2, C3, not all 0, such that the sum is the 0 vector. And so by definition, that means that x1, x2, and x3 is a linearly independent, I'll just write it as linearly dependent set of vectors. Let's look at another example, but in this case, you notice that I've just left off the 3, 2 vector, and now this set is linearly independent. Why is that true? Well, in this case, what I'm arguing is that using only these 2 vectors, there is no way for me to leave the origin and arrive back at it using only the second vector, since I only have 2 here. So let's look at the vector 1, 0. Well, if I leave the origin using the 1, 0 vector, then I'm either going to go right or left. But then I have to discard or get rid of that mode of transportation and only use the 0, 1 mode of transportation to try to get back. But we see that this mode travels left and right, but this mode of transportation only moves up or down. So there's no way I could leave the origin by moving left or right. So let's just say that we take 2 times the 1, 0 vector. So I've left the origin. I have a non-zero multiple of the 1, 0 vector. And now I can't use that mode of transportation anymore. I can only use the 0, 1 vector. Well, now I can only travel north or south, but I need to travel west, given only these two vectors. And there's no possible way that I could only travel up or down and get back to the origin. So this guy here, I could either go this way or I could go this way, but 0, 1 cannot move to the left or right. And therefore, the only way that I could add up multiples of these two vectors, something times 1, 0, let's put a little box here, something times 1, 0, plus something else times the 0, 1 vector, and arrive back at the origin. Remember, I have to be able to leave the origin and arrive back using only the other vectors if the set is linearly dependent. But the only way for this equation to be true, and you can kind of see it here mathematically, what times 1 plus what times 0 equals 0, well, it doesn't matter what you multiply 0 by, the only way to get something times 1 to equal 0 is to multiply it by 0. And similarly here, the only way to get 0 plus something times 1 and get 0 is for that constant to also be 0. So in this equation here, if I write this as c1x1 plus c2x2, and I ask myself, what are there constants, c1 and c2, not both 0, such that this equation is true? And the answer is no, there aren't. The only way for this equation to be true is if c1 equals 0 and c2 equals 0. Sometimes you'll see that written as c1 equals c2 equals 0. That just is a more efficient way to write that out, so that you don't have to write 0 twice. You save a little bit of step there. And therefore, x1 comma x2 is a linearly independent set of vectors. So in a nutshell, that's what linear independence means. It has some far-reaching implications, but for now we're just trying to understand kind of what this idea is. And now we'll look at this definition. And you notice that this definition is really just an extension to, well, these vectors don't have to be in 2 dimensions, and there don't have to just be 2 or 3 of them, there could be 30 of them. So given a set of n vectors, okay, so this could be 10, 20, 30, and we list them out as follows. We say x1, x2, and dot, 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 however many there are, all the way up to xn. The set is said to be linearly independent if the only scalars, c1, c2, cn, right, because each vector is going to get scaled, that satisfy the equation c1x1 plus c2x2 plus dot, 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 plus cnxn. You can see that that's really just a more general, broader version of what we've done in these last two examples. If the only way for that to equal the 0 vector are where c1 equals c2 equals basically all the coefficients are 0, then the set is linearly independent. However, if on the other hand it is possible to find constants that are not all 0, okay, that's the operative phrase here, not all. So if you have one of them to be 0, that's not a problem. It's just, we just want to make sure that they're not all 0 in order for us to call them linearly dependent. And lastly, to just associate a picture with this, now we're drawing this in 2 dimensions, but these could be vectors in 30 or 55 dimensions, or 100 dimensions, or however many, but the idea kind of remains the same. If your vectors are linearly independent, then if you leave the origin, with say 2 vectors, then there is no way to get back. using just scalar multiples of those vectors. They would be linearly dependent if, now you would really need 3 vectors possibly for them to be linearly dependent. So if you had 1, 2, and then a third one, then you could get back to the origin by using that third multiple. Here's another way they could be linearly dependent, is if your vectors were scalar multiples of one another. So perhaps one of them is, say, the vector 5, 0, but then let's say you also have the vector 1, 0. Well, we see that 1, 0 and 5, 0, oh, that's not 5, 0, excuse me. We'll say this is the vector 5, 5, 5, let's say. And then let's say we had another vector 1, 1. Well, 1, 1 is just 1/5 of the 5, 5 vector. So what I could then do from there is, to get back to the origin, I could take -5 times the 1, 1 vector, and we see that if we take one multiple of the 5, 5 vector away from the origin, but then we add -5 of the 1, 1 vector, we get the 0 vector. And you can see that's another way for just 2 vectors to be linearly dependent.